So let's say you were asked to solve a sort of a problem. Let's say you were given some information about a thing. Let's say that you had a number of nuclei at 0 of 10,000 like nuclei. You had a half-life of, let's say, 5 seconds, and you wanted to know what is the number of nuclei of t when t is equal to 0.2 seconds. And you might say, oh, that's easy. Well, that's easy. I'm just going to do n is equal to n0 e to the minus lambda t. I would say lambda from this, lambda is equal to log of 2 over the half-life, so 0.691 over 5, and I would just calculator, which would help in solving this problem. I should have already been ready for that to start with. So 2 over 5, so 0.139 times t, so times 0.2, and times that by 10,000, and I get 9726. And that, goes on. You go like, oh, okay, that makes sense. What if I asked you to do that and didn't allow you to get the calculator? How would you work it out? Could you work it out? Well, it's difficult. Even the most mathematically happy amongst you might find it a bit difficult, or say, well, how do you work out something like this if you don't have access to a calculator? And the old-fashioned way is to use things called log tables, which is essentially where people work the answers out for lots of these things and just plug them into books. So they would just so you were the calculator to go and look up what the answer was. It's quite an interesting problem as to how these numbers are worked out, and takes time for you. It takes time for your calculator as well. The more complex problem you give a calculator, the longer it takes. Imagine doing that over huge, vast quantities of data. Well, that takes time, it takes energy. These things don't happen. So the aim of this is not really to show you something that is like better. It is actually demonstrably worse. We're going to get a worse answer. We're not going to get the correct answer, but we're going to get close enough. And the reason for this is called iterative modeling, because often in science and in physics, it's not about getting the correct answer. It can be about getting an answer that is close enough. And this is the first sort of example of how people do this and build models and go, yeah, okay, I'm happy with that number. So let's see if we can get an answer as close to this, but without having to have used the exponential decay. Right, so let's say, right, okay, well, if we go, let's start with our definition. We know that the activity of any sample is equal to the change in the number of nuclei over a unit time. And that is equal as well to minus lambda n. So this is something that we know. It's kind of the defining equation for radioactivity. Well, what this allows us to do is let's make an assumption. Okay, let's assume that in the time delta t, that the activity is constant. Now, this sentence is not true. This is a false sentence. But this is fair if our change in time is much smaller than our half-life. Okay? Because actually, if you measure the decay of a radionuclide that's got a half-life of billions of years, well, if you measured that for 24 hours today and you measured it for 24 hours tomorrow, you're not going to notice any really big difference. You're not going to notice a decrease in the activity if you've got a really long-lasting thing. So this, as we're going to see, is not an unfair assumption to make as long as this bit in brackets is true. Okay, as long as we do that. So what we can do is we can say, okay, what does this allow us to do? Well, that allows us to say that if we define the change in number as the decrease in nuclei, this means we can just ignore the minus sign. So instead of standard by saying delta means just change, we're going to say it's explicitly a decrease. So we're going to build that minus sign into the delta n. So what we're going to do is we're going to say, okay, that means that our change in the number is going to, or our decrease is going to equal lambda n delta t. We're essentially treating this delta n over delta t as a fraction. Okay, so that becomes our decrease. So what we can do is we can, and therefore our new number of nuclei will be as follows. So n, I'm going to call this 1. So our first sort of value is n0, so our initial start point, minus lambda n0 delta t. So let's do that. We know that n0 is, we've got 10,000, minus lambda, which we worked out, 0.139, okay, times delta t times 0.2. It's minus, so we've got 10,000 times 0.139 times 0.2. And what does that equal? 139. Ooh. So that becomes 10,000 minus 278. 9722. Now, how does that compare with the answer we had in 9726? We're only 4 out. I'm not bothered about 4 nuclei. Now, what does this enable us to do? Well, we might say, oh, okay, this is nice. This works. This is a lovely thing. What would happen if we doubled our time period? Let's say instead of our time period our delta t being 0.2, let's say it was 0.4. Okay, what would have happened? Well, what we can do is we say, oh, okay, let's use this again. So we would go, oh, well, n at 0.4 is going to equal n0 minus lambda n0 delta t. So this becomes 10,000 minus 10,000 times 0.139 times 0.4. So 10,000 0.139 times 0.4 gives us 556. So we do 10,000 minus 556, and we get 9444. Now, what do we get if we do the exponential version? We would have n at 0.4 is equal to 10,000 times e to the minus 0.139 times 0.4. Minus answer, and we get 9459. Now, here's something that's important. Okay, suddenly by going from if our time interval is 0.2 seconds, well, happy days, we're only 4 wrong. But if our time interval is 0.4 seconds, well, look how wrong. Look at our difference now. We're now 15 wrong. By doubling our time difference, we're now a lot more wrong. And this can become somewhat ridiculous because if you take it over the timescale of something where there definitely is a half-life, definitely would be a sort of a difference. What would happen if you tried to do this over, over this idea of saying, let's say we took it as being at, let's say we tried to do this for 2 seconds. Okay, we would have 10,000 minus, 10,000 times 0.139 times 2. So 10,000 times 0.139 times 2. We would have 10,000 minus 2,780. So we'd have 7,220. Whereas if we did this the exponential way, we'd end up with times e to the minus 0.1392. We'd end up with 7,573. And suddenly, oh look, we're now 350 out, which is not, I mean, we're wrong now by about 5%. We've got a 5% accuracy. So this is starting to become less helpful. And this is because actually the problem is that this is assuming that throughout the entire 2 seconds, we would have had a constant decay, which we wouldn't have done. So we end up overestimating how many have decayed. So although it was fine up to here, it then seems to start being less useful. But the reason it's called iterative modelling is actually, instead of just having bigger jump, instead of trying to find a magic point where we're okay with our timescale jump and going, well, how far out can we do it? What we do is we just repeat things. So instead of doing it this way, I'm saying, I've just deleted everything. But instead of saying, oh, I'm just going to just try a bigger time interval and see how happy I am, what I can instead do is say, actually, I can just repeat this calculation. I can just repeat this, but instead of doing it once, I can, instead of doing it with one thing, I can just do it with a 0.2 time interval. I can do it twice, and it'll still get me to here. So I can then do my second time will actually now equal the number I had minus lambda n1 delta t. And so I can say, okay, so I can do this time 9722 minus 9722 times 0.139 times 0.2. I'm keeping my time scale short again. Okay, so 9722 times 0.139 times 0.2, change of 270. So 9722 my answer, and I've got 9451, which is a difference of only about 8. So I lost 4. I was 4 under this time. I was 4 under this time, but I'm much closer to that than I would have been. And if I want to get to n is 2 whole seconds, I just have to keep doing this. I just have to keep repeating this process. Now there are advantages and disadvantages. Obviously, with this, I'm going to end up having to do this calculation a lot. Okay, but I'm only having to do a simple one. I don't have to do anything that involves calculations involving exponents. I'm just doing simple, the simple mathematical devices, which is nice. Whereas this, although this gets me a very accurate answer, this is hard. Imagine doing this without a calculator. This is difficult. And so what we can do nowadays, and this is more now done within a spreadsheet, is we can set up something to do this iterative modeling. So let's load up a spreadsheet. Here we go. I've got a spreadsheet right here. Now, this is shared with you, so you can have a play with it. You can deal with your numbers stuff. But let's say, what do we say? We said the half-life was 5, and we're measuring a time interval of 0.2. Okay. And what I've got here is I've got this sort of spreadsheet that's going to do this. So my time starts at 0, but every time I go down, it's just going to add my time interval, so what I'm increasing my unit of time interval, to this number, so it just keeps going up, which is nice. So as you notice, whenever I change this, I change 0.4, there we go. It's going to recalculate all the times I've got. What I then have here, I've got the ability to set the half-life of this, and I've got my initial number. And this column here is my iterative model. So what you'll notice is that for each successive row, what it's doing is it's doing this equation. It is taking the value it had in the last time interval and subtracting that by the value multiplied by the decay constant multiplied by the time interval, which is this number here. So it's just doing that constantly all the way down. What I've got here is the exponential calculation. So this is the radioactive, sort of like, the true radioactive one. And what we will get is this ability. And what we'll see in this graph, it plots the two things. And what you'll notice is that the iterative model starts to slowly pull down below the exponential decay model. Now, as my time interval goes up, if I increase the unit of time that I'm going to use in my iterative model, what will happen is these two things will agree less and less and less. So if I go to 0.8 seconds, you can start seeing it drop away a lot more. If I go to 1 second, then there is starting to be an actually potentially significant difference, depending on what I've got. Let's go to, let's put 45,000 in. 45,000. So it's nice. It just rescales everything. Now, again, you might sit there going like, I don't get what the problem is, but in terms of why is it such a why is there such a huge issue with this? It's just that this is more an example of showing how this stuff can work, and that this although this might involve this might seem like more fiddly and having to do this, it's a heck of a lot simpler to do that calculation than it is to throw in exponents. Because if you didn't have your calculator, I'm not sure you'd be able to work out any of this. All these numbers would be beyond you, possibly. I mean, I can't remember how I would do it. So I'd have to go and look up how to calculate these things. And I'm aware of tables of integrals, tables of logs. You'd have to go and look up numbers in a big table. But even that, it's difficult mathematics to just generate these numbers. But what we can do is generate them much more simply this way. So yeah, this is the power of iterative modeling. What might this be in terms of the exam questions? Well, they just ask you to fill one out. So they give you a gap and say fill it out and see where it goes. And there we go. That is iterative modeling.